Hello everyone, this is Enem Safarai, and in this video, in the framework of Reinforced Concrete Fundamentals course, we are going to discuss about a singly reinforced rectangular section in bending at ultimate limit state. As you know that when a beam is loaded, we have a simply supported beam, is loaded with a permanent action and a variable action, then it will start to bend. And in the midsection, where the bending will be the biggest, we can have this type of diagrams. We have the section, and as you know, at the bottom of the section, we have the steel reinforcement, which will be denoted by AS. The width of the section will be called as with letter B, and we have the height of the section, which is denoted by letter H. And the effective depth, which is basically the distance from the top of the section till the middle of reinforcing bars, will be called as effective depth and will be denoted by letter D. The neutral axis, which is denoted by NA, will be the line that separates the part in compression and the part in tension. So at the neutral axis, the stresses will be 0. Then for the strain diagram, strain of steel is variable, whereas the strain in concrete will be limited to 0.0035. For the stress block, we will have two types of forces. The force which is developed at the middle of the stress block, which will be the force of concrete in compression, and the force of steel in tension at the bottom, because the bending of the beam will induce a resultant tensile force, as we said, and a resultant compressive force in concrete, which will be FCC. So in order to be in equilibrium, the applied moment, which will be denoted by MED, must be balanced by the ultimate moment of resistance of the cross-section, which is MRD. In the stress block, the other dimension will be 0.567 FCK, which is one of the parameters that we are going to use for calculating the stress block, as well as S. So what we should know that the distance between FCC and FST will be also called as lever arm. So the ultimate moment of resistance will be equal to MRD, and it can be equal to either force of concrete in compression times lever arm or force of steel in tension times lever arm. FCC will be equal to the stress, which is a characteristic strength of concrete, or it can be calculated as 0.567 times FCK times the area of action, which basically it is width of the section times the S, which is the other dimension of the stress block. The lever arm from the figure will be equal to the effective depth minus S divided by 2. A very important parameter to be taken into account is the variable K, which is equal to design moment divided by BD square FCK. If the K value is smaller than 0.167, then there is no need for compression reinforcement, and we say that we have a singly reinforced beam. If the K value is bigger than 0.167, it means that the section cannot carry the load only when we are using tension reinforcement, but it also needs compression reinforcement, or it needs for the cross-section to be bigger. That's why we say that when K is bigger than 0.167, we have a doubly reinforced beam. Then the force of steel in tension will be equal to this value, 0.87 FYK times AS. 0.87 comes from characteristic strength of steel divided by steel material factor, which is 0.15. So gamma S will be 1.15. The area of steel will have this formula: applied design moment divided by 0.87 FYK times Z. And the formula for calculating the lever arm will be found from this one: effective depth times 0.5 plus 0.25 minus K divided by 1.134. All of it will be in square root. So this is all for explanation of the singly reinforced. Now let's go for the problems. Let's see the problem number 1. The ultimate design moment to be resisted by the section in the figure is 185 kN/meter. Determine the area of tension reinforcement, AS, required, where characteristic material strengths are FCK 25 N/mm² and FYK as 500 N/mm². The section in the figure has an effective depth of 440 mm and the width is 260 mm. So we are required to find the area of steel, or AS. So the formula for using AS is basically the applied moment divided by 0.87 FYK times Z. But what is unknown in our formula is letter Z. So the lever arm, the formula to be applied is this one, which are denoted by number 2. So Z is equal to effective depth times 0.5 plus 0.25 minus K divided by 1.134. So in this formula we know D, but we do not know K. For this reason we should start with the value of K, which is basically the applied moment divided by BD square FCK. So if we make the calculation, firstly, do not confuse the units. We are given the moment as kilonewton-meter. That's why, since we are using all the units in millimeter and newton, we need to multiply this one by 10 to the power of 6, which is basically 10 to 3 times 10 to the power of 3. One comes from conversion of kilonewton to newton, and the other one comes from meter to millimeter. And as you can see, the value of K is 0.147, which is basically less than 0.167, and we are going to design this beam as singly reinforced. After finding K, then we can go up and calculate the lever arm, which will be 373 millimeters, and then we go up again and we can calculate the area of steel, which basically will be 1140 millimeters square. So in order to convert this area of steel into number of bars, basically what we do is we apply this simple formula. We know that the area of a bar is the area of a normal circle. So basically we are writing as N, which is the number of bars that we are going to use, 3.14, which is the P letter, and diameter square divided by 4. We need to make one assumption first, what type of bar we are going to use. So in this case we are using a 20 millimeter diameter bar. So if we make the conversion, then we're going to find that we need 3.6 bars. So what is interesting here is that we can provide 3.6 bars, but we cannot have 3.6 bars because we do not cut the bar into pieces. That's why we are going to round this value up into 4. So we need to provide 4 bars with the area that will be 1260 millimeters square. And we write this one as 4H20. So for the bars, hot rolled steel bar, we write it as letter H. This is for problem 1. For problem number 2, we have a different approach. We have analysis of a singly reinforced rectangular section in bending, and we are required to determine the ultimate moment of resistance of the cross-section shown in the figure below, where we are given the material characteristic strengths of 500 N/mm² for steel and 25 N/mm² for concrete. The section in the figure is this one. We have the width, which is 300 mm, and the effective depth is given as 520 mm, and the area of reinforcing steel is 1470 mm². So in this type of problems, what we are required to know is that how much the neutral axis extends on the section. For this reason, we need to draw the stress block that we explained in the previous video. So we have the force of concrete in compression and the force of steel in tension, which are extending on top and at the bottom of the section. Then we have the components, which are the 0.567 FCK and the S on top, and in steel we have only the force. So it is very important to draw the stress block and to find the depth of the stress block, which is denoted by x. However, there are some mistakes that generally students go for directly using the formula from letter k, which is MED divided by BD square FCK, and they take the maximum value of k, which is 0.167. If you do this approach, then we would find this value, the design moment to be 338.676 kilonewton meter, which is not the right approach. If we solve it on the other way, then we will see that this value that was previously calculated is much bigger than the one that is the correct answer. So in this type of questions, what we should do is that from equilibrium, we need to balance the forces of concrete in compression and the force of steel in tension. The formula for FCC will be basically 0.567 times force of concrete in compression times width times S will be equal to 0.87 Fyk and As. The only unknown variable here is the letter S. For this reason, if we take this out, we'll see that the value of S will be 150 millimeters. Then we find x, which is the depth of the neutral axis. Basically, it is S divided by 0.8, and x will be 188 millimeters. To check whether the steel yields, we need to compare x with 0.617 times effective depth, and we will see that x is much lower than 320, so we are okay, and the steel yields. In order to calculate moment of resistance, basically what we do is we use the formula force of steel in tension times lever R. If we do multiplications, be careful here to calculate Z from the figure that we have drawn. Z is the effective depth, which is 520, minus S divided by 2. So S we found as 150, so if we do all the calculations, the ultimate moment of resistance will be 284 kilonewton meter. In problem number 3, we have bending reinforcement for a singly reinforced beam at the ultimate limit state. We need to calculate the main steel area of reinforcement for the beam in the figure, assuming the following material strengths, which are Fyk 500 and FCK 25 megapascal. So the cross-section in the figure is the width 275 millimeters and effective depth 450 millimeters. We are not given the design moment, but we are given the span of the beam and the variable action Qk and the permanent action Gk, which are 8 and 12 respectively, kilonewton per meter respectively. So we are asked to find AS, and the formula for AS is design moment divided by 0.87 Fyk times Z. So in this formula, we do not know MED, we also do not know Z, lever R. So we start by calculating MED. The formula for design moment will be equal to design load times span squared divided by 8. In this case, we do not know design load. For this reason, we calculate design load first, which is 1.35 variable permanent action plus 1.5 variable action, and we calculated it as 28.2 kilonewton meter. We apply this one in the formula above, and we will calculate design moment as 172.7 kilonewton meter. Then we need to find Z, but to find Z, we need to know the value of K. For this reason, we need to calculate K. And K will be equal to applied moment divided by BD square FCK. We know all the variables here, so we will find that K is 0.124, which is less than 0.167. So we say that no compression reinforcement is required. So after calculating K, we can calculate Z, which is 393.7 millimeters. Then after knowing Z, we can calculate directly the area of steel, which is 1008 millimeters square. So if we assume 20 millimeter bar diameter, Then we are going to provide 4H20, which are 4 bars with 20 millimeter diameter, and the area to be provided will be 1260 millimeter square. In problem number 4, we are required to check a singly reinforced section, whether it is adequate to carry the given load or not. So we have a simply supported rectangular beam of dimensions 300 by 500 millimeter. 300 will be the width and 500 will be the height, which spans an effective length of 5 meters. It is subjected to a permanent and variable actions of 16 and 8 kN per meter respectively, and the section is singly reinforced with 4 bar with 20 millimeter diameter and has a concrete cover of 25 millimeter. Concrete is class 3037 and steel is grade S460, and as I said, we need to check whether it is adequate to carry the load or not. The figure, the cross-section is given as like this. We have 2 layers of 20 millimeter diameter bars to make 4 bars, and we have height 500 and 300 and so on and so forth. So in this type of problems, when we are required to check whether the section is adequate or not, we need to calculate design moment and to compare it with the moment of resistance of the section. If MRD will be bigger than MED, then yes, we can say that the section is adequate to carry the load. So let's go back to the concrete class, which it is given as the grade or the class 3037. As you know, in Eurocode, we are having 2 types of tests. We are having the cylinder test and the cube test. So we are always using, when we are given such the way of representing concrete strength, we are using 30 Newton millimeter square. So we are using cylinder strength. And for steel S460, we are using FYK S460 Newton millimeter square. In the difference of this problem is that we are not given the effective depth, but we are given only the height of the section. So in order to calculate the effective depth, we are using overall height minus concrete cover minus bar diameter divided by 2. Be careful also in this problem, the shear link diameter is not taken into account. Okay, so there is no need to confuse it with other problems. So if you can make the calculations, we have the height, which is 500, concrete cover was 25, and bar diameter was 20 divided by 2. But here be careful, the effective depth will be in the middle of these 2 layers. That's why we have multiplied it by 2, because we have 2 layers of bars. And the effective depth will be 455 millimeters. The procedure that we are following, we make the equalization of the forces because they are in equilibrium. So force of concrete in compression will be equal to force of steel in tension. We calculate S, and then from S we can find MRD, which will be equal to 204.08 kilonewton meter. Then we need to calculate MED, which will be equal to design load. It will be equal to design load times span square divided by 8. Design load will be calculated by using the coefficients 1.35 dead load plus 1.5 live load, and we are going to have 33.6 kilonewton meter, and the overall design moment will be 105 kilonewton meter. Then we can compare moment MRD, which was 204, and MED 105. So MRD is bigger, and we can say that the section is adequate to carry the load. In problem number 5, it is again about singly reinforced beam design, and we are given a problem as a reinforced concrete beam, which is 300 millimeter wide and 600 millimeter deep, is required to span an effective length of 6 meters. The beam carries permanent variable actions of 25 and 19 kilonewton per meter respectively. Design the beam for bending reinforcement using concrete class 30 Newton millimeter square and FYK as 500 Newton per millimeter square. In this question, we are also asked to take into account the self-weight of the section. So in the figure, it is like this. So we are having the beam, which is 6 meters, and the loads that are acting on the beam, GK, which is 25 kilonewton per meter, and QK, which is 19 kilonewton per meter. The first thing we need to deal with is the loading. So for the loading, we have self-weight of the beam. Self-weight will be equal to one dimension, which is the height, times 0.3, which is the width, and 25, it is unit weight of concrete. So at the end, we are going to have 4.5 kilonewton per meter. So the total permanent action, GK, will be equal to 25, which was given in the problem, plus 4.5 that we calculated from the self-weight, which is 29.5 kilonewton meter. And then we need to calculate the ultimate load, which will be equal to 1.35 GK plus 1.5 QK. So at the end, we are going to have it as 68.33 kilonewton meter. Then we can calculate ultimate design moment, MED, by using ultimate load times span square divided by 8, and we are going to have as 307.485 kilonewton meter. The way to calculate the effective depth, this is the correct one. We need to make some assumptions first. We are going to assume the diameter of the main bar, which in this case we are taking it as 25 millimeters. We need to assume the diameter of shear links, which we take as 8 millimeters. And we need to assume also the concrete cover. In this case, we are assuming it as 25 millimeters. So at the end, we are going to have this value, which is 554, which was found out by subtracting from 600, 25, 8, and 25 divided by 2. In order to calculate the main steel area, which is the one that it is asked in our problem, we need to calculate the value of K first. So if we do the division, we find that K is 0.111, which is less than 0.167, and there is no need for compression reinforcement. So we are going to design this beam as singly reinforced. Then we can continue with calculating the lever arm, which is found by this formula. So effective depth times 0.5 plus 0.25 minus K divided by 1.134, this one in square root. And we can find out that Z will be equal to 493 millimeters. What we need to make a check is that if the lever arm is smaller than 0.95 times effective depth, in this case 0.95 times 554 will be 526, so we are okay. Then we need to calculate the area of steel reinforcement, which is found out by the normal formula, design moment divided by 0.87 FYK times Z. And we will find out that the area will be 1433 millimeters square. If we provide 3 bars with 25 millimeter diameter, then the area to be provided will be 1470 millimeters square. And this is the end of problem number 5.